today's class, which is on the simple linear regression model. Yeah, okay. So this is what we're going to look at today. We're going to look at a new topic, which is a linear regression model. So the linear regression model is about finding the relationship between two variables. Okay. So in the linear regression model, okay, we are looking at finding the relationship between two variables, namely x and y. Okay, sorry. Thank you. I always forgot. Okay, yeah. All right. So let's look at what is it all about. Yeah. So it is about welcome. It's about looking at the relationship. All right. Between two variables. So the fact that it is called linear, right, should basically tell you that we are looking at just a linear model. Yeah. So linear model means the powers of the variables are basically linear, so just in terms of power of 1. Yeah, so this is what the topic is basically all about. Okay, so this is what we're going to do. All right, so what we do is we are going to find what is that linear model, that means what is that relationship. And then once we obtain that relationship, we are going to see how good is that model, or how good is that equation that we get. And then from there onwards, we can use that to make some predictions, yeah, of the future observation. Okay, so what is it that we would like to do? Yeah, so basically we would like to investigate, all right, the results of statistical inquiry or experiment by comparing two sets of data. So what we have is we have two sets of data. We normally put that in the form of the x and the y. And these two values, okay, happens
Start the
simultaneously.
new
Yeah.
chapters right
So
now.
for
Okay.
example, let's say if you have
All right. Okay.
a
We are in the heat
reactor that
exchanger
looks at
topics,
the
so
yield,
it's
all right,
only
and your
we have only
one
more
of the
chapters to
variables that
cover all the
you
topics
of
under
interest to
heat
you,
exchanger.
let's say, is let's say the pressure. All right, so you want to look at how does the yield, okay, be related to the pressure. So this is what we have. Yeah, so we have one values for the pressure, one values for the yield. So we are trying to find what is the best equation that will map these two together. And because it is linear, so that equation will just have to be a linear equation. Yeah. So basically, this is what we have. So for example, the age of a plant versus the quantity of fruit. Yeah. That means if we say age and the number of fruits bred by
Share
the
your
plant,
voice
okay, or produced by
to
the
answer
plant,
or to
or the
respond to me.
pupils
Okay.
mark in
That I
ODE
will.
against statistics. Yeah. So that's another
And
one.
then
So we
don't
want to
forget
see
the upcoming
what is the relationship between scoring in
Wednesday.
the
You also have
statistics
to submit
exam
your
and
assignment.
the
I
ODE.
think
Yeah, so whether there's
after
any
I cover
relationship
the
or
heat
not. Yeah,
exchanger
so this
topic,
is
you
what
all can
the
proceed on.
linear regression is all about. So it's just comparing two sets of data, X and Y. Okay, so in order to do this, okay, so what we do is we first need to identify what is our dependent variable and what is our independent variable. Yeah. So for example, just now, if I say you're looking at the yield, all right, that means how does the yield depend on the pressure, for example. Okay. So basically, the yield is your dependent variable. So that's the y. Okay. And pressure is the one that you would like to see. That means this is your independent variable. So we are saying that the yield is dependent on the pressure, or the pressure contributes towards the yield. Yeah. So this is what we call as independent variable. Okay. Right. So what we do is we take a certain number of observation. Let's say when you do out the experiment, okay, or you're looking at the process. So what you do is, let's say you take a collection of 20 data sets. Yeah. So that means your observation is 20. So you will have x1, y1 up to x20, y20. So let's say you have a yield of um, hold on. Okay, let's say your yield is you have y, so you basically have a data that looks something like this. All right, so you have your y and you have your x. So let's say your yield is 20 kg, for example, at a pressure of, let's say, 100. Okay, and then you have 15 kg, maybe a pressure of, let's say, 110. Okay, and then you have 18 kg, all right, maybe at a pressure of 115, and so on. So basically, this will be your observation. So you have n observation, yeah. So this is your n number of observation. Okay, so this is what you do. So you collect data in the form of either X, Y, or YX, doesn't matter, but you have these certain values that you want to see how are these two being related. Okay, so when we talk about a linear model, all right, so the best one that relate between the Y and the X is, of course, the simple equation, which is Y is equal to, if you remember, mx plus c, because your x here is linear. All right, so basically this is what you have. So you're trying to figure out what is this value, yeah? What is this equation? Y is equal to mx plus c. So in this case, what we do is we put it in the form of beta naught plus beta 1 x. So this is your constant, this is the gradient. So what we're trying to do is, okay, we're trying to define what is beta naught and what is beta 1. So how do we get beta naught? How do we get beta 1? So these are called as the model parameters. Okay, that means the intercept and the gradient. And there's so many ways in which we can do this to get the value of the beta naught and the beta 1. But in this regression model, we are just going to use one technique, which we call as the least square method. Okay, so this is a technique that we're going to use. We're going to use the least square method or the LSM. Yeah. All right, why do we want to do this? Because if we know the value of beta naught and beta 1x, then let's say you can predict. Okay, let's say we say that just now, let's say if the pressure is now, let's say 200, so what will be the value of the y? So if you got this equation, so you will get what is the value of the y if you know that the pressure is 200. So this is what we want to do. So we want to get the prediction for y, or sometimes we call it as the expected value of the y. So what would be our expected value if we are given a certain value of the x to get the value of the y. Okay, so this is the whole thing of the regression model. We want to just obtain this equation, okay, hoping that after we got this equation, we can make the prediction, or we can estimate certain values. Yeah, so this is what we do. And how do we get this equation? We are going to use it using the least square method. Okay. So this is what we have, yeah. So what is the relationship? All right. So this is the relationship. All right. So we know that this is the dependent variable, the yi that we take here. And then this is your beta naught, which is the intercept or the, and this is the gradient or the slope. And x here is called the independent variable, and here is what we call as an error. Why do we put an error? Is because we could not actually get the exact equation that is going to fit the x and the y together, because if we have the exact equation, then we don't need to estimate what's the value of your beta naught and the value of your beta 1. Yeah, so this is the whole thing. So we want to find this relationship between the dependent variable and the independent variable. Okay, so this is what we want to find. Beta naught and beta 1 are what we call as the model parameters. Okay. Sorry. Okay, so how does it work? Yeah, so basically this is what we do. So this is the actual relationship. Remember, this is still an inference, yeah, because we don't deal with the whole population. All right, so we're just dealing with this unknown relationship of y is equal to beta naught plus beta 1 xi plus the error. So what we do is we take a sample. Yeah, from that sample we estimate what's the value of your beta naught hat and the value of your beta 1 hat, so that we can say that the beta naught hat will actually be estimating the value of the beta naught, and the beta 1 hat will actually be estimating the value of your beta 1. Okay, it's just like the mean, mu and the x bar. Yeah, so we say that because the mu is not known, we use the x bar to estimate the mu. So same goes with this situation. So what we're doing is we are just trying to estimate this, okay, so that we know that what is we think is a suitable value for the beta naught here and the suitable value for the beta 1 here. Yeah, so we deal with this. So that's why we take just now 20 observations, because from that 20 observation, we are going to estimate the value of the model parameters. Yeah, and that we say that this equation will be basically the representation of this unknown relationship. Yeah, so this is what the whole thing is all about. Okay, so how does the simple linear regression model look like? Yeah, okay. So what we do is we are basically doing this situation. Okay, what is this least square method all about? Yeah, okay. So if you look at this, all right, this value, the dots, the not the dot, the circle here, yeah, the full circle here. All right, all this, this circle, all these, the circles here are all the value that is basically observe, yeah, whenever you carry out the process or whenever you do your reactor calculation. Okay, so but what we do is, okay, we just take a certain values, so we, these are the sample values that we take. So what we do is we're taking the full circle here. So these are the values. Yeah, all right. So what we do is we, once we plot all these values, we are trying to find, all right, how can we use this value, all right, to correspond or to find the relationship between the x and the y. This is our objective. Okay. Now, when we do, what we are doing is, okay, how do? We just estimate a line. So this is the line that we are trying to get, our beta naught hat plus beta 1 hat that we are estimating. So this is the line. But because this line is just an estimate, yeah, all right, so there will be some error. Error in the sense that uh, this is the actual value, but your line says that it is just here. So basically, if you base it on your point, this is the point that you get based on your equation. All right, so this is the error. That means this is the error that you need to encounter, or you need to basically consider whenever you do this estimation of the line. Okay, so because of this error, all right, we need to find a way to make sure that we can be able to maximize this error. Sorry, minimize this error, not maximize. Yeah, all right. So how do we do this? Is just by looking at if you are able to minimize this error. So what we are saying is that our line will be as close as possible to the observed value. So that means if we can minimize this distance, all right, or this distance, all right, this distance, yeah, that means if this distance is small, so we are saying that the observed value and the line, yeah, is actually a good fit, meaning to say that we have made sure that this line is actually as close as possible to the observed value. So this is what we are doing. So this is what the least square method is all about. Yeah. So what do? We do this. That means best fit here means the difference between the actual value and the predicted value is minimum. Yeah. So because it can be up and down, it can be the points can lie above or below the line. So we have positive and negative. So for that reason, we have to square all those errors. So this is what we are doing. All right. So the whole idea is if we can minimize this error, so then we'll say that our line will be a good line, or our line that we obtain is a good fit. All right. So this is the actual. This is our predicted. Remember, our predicted is always given by the y hat. Yeah. So if this error is minimized, then we will say that this is a best fit. So when we say that the actual y and the predicted y is a minimum. So this is what the least square method is all about. Okay, the LSM. Okay, so the LSM is just looking at the difference between the observed and the predicted, and to make sure that this is minimized. So based on this technique, we will derive, okay, we will get from here what is the beta naught hat and what is the beta 1 hat. Okay, so based on this, yeah. So we'll do the mathematics behind it, all right, then we will come up with what is the beta naught hat and the beta 1 hat. So basically, this is what we do lah. So what we're doing is, if this is the line that we actually predict, so we are minimizing this error. Okay. So because the error can be positive or negative, so we square that. Just like in the ANOVA, remember? We say that some is above, some is less. So for that reason, if you don't square it, you may end up as being zero, yeah, when you sum up everything. So for that reason, we square this. So this is how the least square method works. Okay, so now how do we do that? Okay, this is how we do it. That's the mathematics of it. So what we do is, because we want it to be minimized, so what we do is we take the differential, all right, with respect to the x and whatnot. Okay, then we find what are the values. Yeah. Okay, so this is the one that we want to predict. This is our equation. So we say that this is our predicted equation, which is the beta naught hat and the beta 1 hat. Okay. Right. So how do we do that? We're going to take that from the sample. So how do we get the value of the beta 1 hat? Is just by this equation. Okay. So how do we get this value? What we do is we take this equation. We take y minus y hat squared, and then we do the differential with respect to x, then we will end up with this situation. Okay, right. So the beta 1 hat is given as sum of squares of the xy, all right, divide by sum of squares of the x. All right, then how do we get sum of squares of the xy? This is the formula that we use. And how do we get the formula for the sum of the squares of the x? This is a formula that we use. All right. So we put this in this beta 1 hat formula, then we'll be able to get what is the value of the beta 1. So we know what is our beta 1 hat. Okay, that means we know what is this value based on the minimizing of the error, which will end up with this formula. Okay. But now, once you know the beta 1, you need to know the beta naught. So how do you get the beta naught? The beta naught is given by this. Right, is the value of the y bar minus the beta 1 x bar. So this is how we get the value of the beta naught hat. So once we know beta naught hat, we know beta 1 hat, then we know what is the equation. So the equation is just given by y hat will be equal to beta naught hat plus beta 1 hat xi or x1 in this case. Okay. So y bar is of course the average of y, and then x bar is of course the average of the x. Yeah. So this is what we have. Yeah. So this is what we're going to work on in order to get the value of the beta naught and hat and the beta 1 hat. Okay. So what do we do? Yeah. So in order to do that, all right. So we have all this observation. All right. X1, X2, right up to Xn. So to calculate the coefficient equation, that means to calculate what is beta naught hat and beta 1 hat. So we need to create all this table lah, because we are going to use the formula. So we have X, summation of X, and then Y, summation of Y, summation of XY, and then summation of X squared. Why do we do this? Because we need to fit in this formula. Yeah. Because you need the beta 1 hat, you need the summation sum of squares of the xy, and to get the denominator, you need to take the sum of squares of the x, which basically gives you this. Yeah. So this is summation of x the whole thing squared over 1 over n. Okay. So this is what we have. So normally we do this in the form of the table, then only we calculate the values and we put that in the equation. Okay, then once we get that, so we estimate using this lah, which is basically the sum of squares of the x and the sum of squares of the uh, xy over sum of squares of the x and over this. Okay, sum of squares over there, yeah. Okay, so this is very mechanical, yeah. All right. So for example, yeah, it says here, the manager of a car plant, all right, wishes to investigate how the plant's electricity usage depends upon the plant production. All right, so this is the data that is given below to estimate the regression equation. All right, okay. So what we have here is just a situation where we think that the electricity usage depends upon the plant production. So in this kind of situation, you need to know what is your dependent and what is your independent. Okay, so here the electricity usage depends upon the plant production. So electricity usage will have to be your Y, and this one will have to be your X. Okay, so even if it's not mentioned to you which is your X, which is your Y, you should be able to figure that out. Okay, so this is the situation that you get. Right, so these are the values. Yeah, and then from here you want to estimate what is the equation. So the first thing that we do, yeah, before we estimate, yeah, anything, yeah, before we do the regression equation, so what we do is we always plot first. Okay, we plot what we call as a scatter plot. Okay, so why do we plot a scatter plot? The reason is this. Go back to the blank slide. Okay, the reason why we plot the scatter plot is this. All right, first, your X and your Y. Okay, the reason to this is because we want to see whether is it possible to have a linear relationship or not. For example, let's say if you plot all the X, okay, these are the points. Okay, the points can be scattered. Does it matter? All right. So if you look at this situation, yeah, then you see that okay, you know, you seem to notice that when your x actually increases, the y is actually increases and it's actually going in one direction. The trend is going in one direction. So you feel that since it is within this context, yeah, so you feel that yes, if you fit a line, it's possible for you to fit a line. All right, doesn't matter how you fit a line, but you think that you can fit a linear equation. That means you say that yeah, there's a possibility of an equation of the form of y is equal to beta naught plus beta 1 x. Okay, so this is what we want to determine first. So that's why we draw the scatter plot. Because if you think that you cannot fit a linear line, all right, then there's no point for you to do the equation. All right, so for example, all right, like this, you think, okay, yeah, it's possible for you to have this equation of y is equal to beta naught plus beta 1x. Let's say you have a graph that looks something like this. Yeah, sometimes from the equation you may get, okay, this is your x and this is your y. You may have a graph that is, you know, like totally out, meaning to say that, you know, your points are like so scattered. All right, so if you have a points that's so scattered like this, all right, no way you can fit the line of y a linear equation. So forget about doing the linear equation. That means this is not going to work because you know that the points are too scattered. Yeah, or sometimes you have equation that tells you that, you know, some points may make you, you know, you can have a curve, something like that, you know, sometimes. All right, so you think that it's better to fit a line in that manner. All right, so that's why we say that okay, this linear equation will not work. So that's the reason why we do the scatter plot, to see whether there is a possibility of doing the linear equation or not. So basically this would be the first test that I normally do. Yeah, so I normally do, the first one is I draw a plot. All right, I run the plot in the Excel to see whether yeah, there's a possibility. So it can go up or it can go down, depending on the gradient. All right. So to see whether there is a possibility of having a linear relationship to be fitted or not. Okay. Before I move on to basically calculate the beta naught and the beta 1. Okay. So this is what I normally do first. Okay. All right. So in this case, all right, so if I plot this, I should be able to get something that tells me that it's possible to fit the equation. I didn't plot for this one. All right, okay. So the next thing now is, because it says here you want to estimate the linear regression equation, so you basically want to find what is this equation. What is beta naught hat plus beta 1 xi, okay? So identify your x, identify your y. All right, then we do it. Okay. All right. So this is what we have. Yeah. So I draw up the table for the x, for the y, for the xy, and the x squared, and I find the summation here, because at the end of the day, these are the values that I want. Yeah. So summation of x, you sum up everything. Summation of y, you sum up for the y. Xy means this multiplied by that, right? You sum it up, okay, and so on. Yeah, so you get this value, and finally you get summation of x squared. They all this because you want to use that in the equation, yeah, that you want to define. Okay. Move. Hmm. Are you having this problem? You, is it lagging? Okay, no. Okay. All right. So this is what we do. Okay. So to estimate the beta 1 hat, you can't hear me? Can you hear me now? Yeah. Okay. All right. Kalau tak boleh dah, I think you kena log in and log out kot. Okay. Okay, so we want to find the value of the beta 1 and the beta naught, yeah, because eventually we want to find the equation. So find what is our beta 1 hat first, all right, just by using this formula, so which is the sum of squares of the xy divided by the sum of squares of the x. So basically we need to work this out lah. What is summation sum of squares for the xy? So that means it's just taking summation of xi yi minus 1 over n summation of xi summation of y. So you get a value that is 2.43045. Okay, then we get the denominator, sum of squares of the x. Yeah. So again, just put in the value. Yeah. Summation of the whole lot square first, and then summation of xi, the whole thing squared. So this one is actually up here too. All right. So this gives you 4.8723. Yeah. Then we put inside this, so we will end up with this. So that means this is now the estimated slope, okay, or the estimated gradient, 0.4988. Then once you know the beta 1, you can figure out what is your beta naught hat. Okay, so the beta naught hat is given by y bar minus beta 1 x bar. So y bar, all right, minus beta 1, which is the value of whatever you got earlier, x bar. So that will end up with a value of 0.4091. So your estimated regression line is basically equals to this. So what you're saying is that the electricity usage, all right, is actually can be calculated from 0.4091 plus 0.49888 value of x. So what you are saying is that in the case where your production is zero, yeah, your the dependency of the apa tu your y is actually 0.4091, yeah, and this means that if you hold the other values constant, your y will actually be having an increase of 0.4988 for each value of the x, whatever that you put here, whatever the value lah, kilowatt ke watts ke whatever. So this is what we have, yeah. So this is the equation that we are looking for based on the table that we got earlier. My slides do not move. Okay. Yeah. All right. So okay. So based on this value, yeah. So I feel that okay, the electricity usage is dependent uh, on the production. All right, how much you produce based on that equation. So this is what I want to do. So this is the equation that I got. So any questions? Ada soalan? Ada soalan? No. Okay. All right. Do we need to calculate the error? No, we don't. No. No, we don't, because we have minimized the error. Okay. Because we have minimized the error. So for that reason, yeah, we don't need to calculate. Okay. All right. So this is what we do to get the value of the beta naught and the beta. How minimize? Oh, because we use the least, sorry, we use the least square method. Okay, hold on, eh. Okay. Because we use the least square method, yeah, we use this. Um, we use this. We use this technique, okay, because we minimize this. Okay, we say that the difference between the actual y values and the predicted y values is minimum. So that's why we minimize this error of it. That's how we do it. Okay, hold on, I'm getting the IT people to see. Okay. So this is how, because we minimize this. So what we do is we minimize the actual with the observed, with the fitted one. Yeah. So this is our actual value y that we plot. So basically this is what we do. All right. So we have these are the y values. Okay. Assuming this is the y values, and we fit this line. So what we do is when we use this square method, we minimize these distances. This error is already minimized. So when this error is minimized, then we say that the line is almost close to getting it. Yes. 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 The equation that we get will be the best fit linear equation based on the data. Okay. Uh, uh, yeah. Do we need to do this to show the scatter plot? It's good to show because if, like I said, yeah, you don't have a linear relationship, then why do the linear relationship? Need to check in Excel? Yes. Yeah. Yes. I would strongly suggest to use Excel. Okay. Strongly suggest. Okay. To use Excel. Yeah. Okay. So that we do that. Yeah. So I would strongly suggest, because it's a lot of things that you are going to do. I would strongly suggest for you to use the Excel. Okay. So Okay. So no questions on how we get the model. Okay. All right. So what do we do next? Okay. All right. So remember, so what is our objective? Okay. So this is our objective. Okay. Number one, get the equation. Okay. Get the equation. So once you got the equation just now, your y hat equals to beta naught plus beta 1 x. Okay. X1 or xi, whichever lah. Yeah. Okay. So the question now is, after we get this equation, what do we do? Okay. So we need now, okay, we think that this is the best equation that we get, all right, based on the data. But does this, because we estimated the value of the beta naught and we estimated the value of the beta 1, the question now is, can we actually say this equation is good or not? All right, that means it's not enough for us to get the equation. So maybe because the data that we get this equation, but this equation doesn't actually tells you that this is the best equation to model that relationship. All right. So what do we do? So because of this, it's not enough. So we now have to do an assessment. Okay. So we have to do an assessment. Assessment of what? Assessment of this model. That means, is this model that we get okay or not okay before we use that to predict, let's say now just now we got like that value, yeah, for the electricity and the production. So before we use that to say, oh yeah, okay, we can predict the uh, electricity based on this production, before we fit in the value, we need to know whether this model is acceptable or not. Maybe our data is wrong, so that's why we got this model. Yeah, so what do we do? So we need to do this assessment. But because we use the LSE, that means, sorry, the LSE, the LSM, the least square method technique, yeah. So all our assessment will have to be based on the least square method technique, because you cannot be using other form of assessment, yeah, because your model is based on that least square method. So we need to use that least square method technique, yeah, to basically do the assessment of the model. Okay, there are five actually assessment of the model. Number one is the standard error. Okay, number two is measuring the strength of the relationship between the x and the y. Okay, number three is what we call as the hypothesis test, to test for the value of the slope. Okay, number four is the confidence interval. And the lastly, number five is the ANOVA. All right, so the ANOVA is the same concept as what we learned in the last class, yeah, in the last chapter. Okay, so, but we're not going to do the confidence interval. What we're going to do is we are just going to look at three possible assessment first, then only followed by the ANOVA. Okay, so this is what we're going to do, yeah? All right, so these are the assessment. That means how good our model. If they pass all these tests, okay, then only we say that that model of y hat that we get just now, okay, this model that we get is a good model. Okay, so this is what we get. Yeah, yeah, so this is what we're going to do. Okay, so let's look at two techniques first, yeah, for today. All right, then we'll do the t-test and the ANOVA later. Okay. So what is standard error? Standard error is actually standard deviation. All right. So this is the standard error or standard deviation. So if our standard deviation, yeah, between the observed and the predicted is small, that means our matching is good lah. So meaning to say that our model is good. Yeah. Okay. So this is what we want to look at. Okay. What is coefficient of determination? Coefficient of determination tells you how strong is the relationship between the x and the y, meaning to say how much is actually y dependent on x. That means x ni contribute how much to the value of the dependent variable. So that is our coefficient of determination. The t-test and the ANOVA, we'll look at that later. Okay. So remember, yeah, the standard error is a standard deviation. So the smaller the standard deviation between these two, all right, that means the smaller the error, the better lah. That means to say our line is a close fit. So we are looking at a small value, yeah, of the standard error, uh, or else then these IT people asking me to do a lot of things. Give me 5 minutes, yeah. Okay, so this is what we're going to do. Okay, look at the standard error. If you look at the standard error, is actually the value of the square root, yeah, of the sigma squared, tertinggal the sigma squared, all right, the square root. So this is basically the standard deviation lah. So we are looking at the value of the sigma squared. Okay. Now, how do we get the standard error, or how do we get the value of the sigma squared? Is given by this SSE, all right, divide by n minus 2. Now, what is SSE? What is the error? The error is the difference between the observed and the predicted. Okay, this is our actual value. Okay, this is the one that we predicted using the equation. Yeah, so this is how we calculate the error. That means the difference lah. If they deviate too much, then that means your data is very far apart lah from the observed and the actual. But if they're close, that means to say that your fitting too is very good. Yeah. Okay, so we are looking at SSE divide by n minus 2. Okay, this is a standard formula that we use. Yeah. Okay. So because of this, that means we want to be the fitting to be close. All right. So we want this value to be small. So we're looking at a small value. That means we do not want it to be too much deviation. Yeah. Okay. So how do we calculate the SSE? You have a choice. Either you calculate by taking the observed minus the predicted. That means, let's say, how do you get this? Let's say if your x is, let's say, a value of 100. All right. So you have your y, you have your y hat. Okay, and then you have the difference lah. Okay. So let's say when x is 100, let's say the value is 20, for example. And then how do you get the y hat? You put back in the equation yang you dapat tadi lah. You substitute in y hat is equal to beta naught hat plus beta 1 hat. Okay, so let's say you get a value of, 18.5, for example. So the difference will be 20 minus 18.5. So that will give you 1.5. And then you square this deviation. So you have d squared. Then you sum up. Okay, you can use this formula or you can use this formula. This is a formula that's given to you, which will also give you the sum of squares of the error. So this is sum of squares of the y, all right, sum of squares of the x, all right, and sum of squares of the x. So this is how we calculate. So if you want the y, so we take y I squared minus this. This one, like the formula earlier, this is the sum of squares of the x. This one ni ada sum of squares ni. SS. Okay, right? So this is how we calculate. To get the value of the SSE, and we divide by n minus 2. What's n? N here is your number of observation. So we have your observation is 12 sets. I mean, that data contain 12 observation. So your n is equal to 12. So 12 minus 2 gives you 10 and you calculate. But what matters is you're looking for a small value of the sigma squared, yeah. So that when this your sigma squared here is small, then the square root will give you a small value. Okay, so this is what we want. So we are looking for this. Okay, we are more concerned with the slope rather than the constant because it doesn't matter, yeah, whether the constant is there or not, as long as kalau the constant is not there, then the line will pass through the origin, kan. If not, it doesn't matter. So what we need to do is we just want to make sure that the slope is the one that matters, because the slope tells you that there is a gradient. All right. So we are looking for a small. The smaller the SSE, the more successful is the linear regression model in explaining why. So what we mean is that if the value of the SSE is small, then we say that our y that we actually obtain is actually a good model. So we want it to be small. So the first criteria of the assessment is the standard error. Okay, or the standard deviation. Okay, so this is what we want first. So in order for it to be a good model, okay, so good model means that, okay, our standard error must be small. Okay, so this is the first criteria. All right, so we're looking at a small standard error. So how do we get the standard error? So standard error is actually the square root of whatever that you calculate from here. Yeah. So that gives you a value of 0.173. All right. So this is the standard error that we get. Yeah. So this is the first criteria that we meet. Okay. Whenever you do the testing of the model, you cannot just look at one. All the four criteria must be telling you the same conclusion to see whether it is a good model or not. Yeah. So you need to make sure that this is the first thing that we do. We want to see how small is the standard error. How small is counted as small error? Quite difficult to say. Yeah. All right. Depends. It actually depends. I wouldn't if you ask me if I just base it on this, I wouldn't say that this is small or this is big. I need to see other things, other part of the assessment for me to actually decide whether this is small or not. Because if I look at the variance is actually 0.02, which is just about 2%, which is actually quite small if I look at the variance. But when I look at the standard deviation, it gives me a value of 0.1. So basically, it says that your data deviates, not data, the error deviates is only about 0.1, between the two values. So I think it's quite small. 0.172 is basically quite small. But I wouldn't want to use this to say that it is a good model or not yet. Do we use the equation of the standard error of the slope? Yes. Yes, we do. This equation uh, what do you mean by do you use equation standard error of the slope? I don't get you. Oh, okay. When to use it? Okay. To get the standard error, we use this formula. Okay. This will tell you the standard deviation that I want. This equation is just to get the standard error of the slope. Yeah. So this is I will tell you when do we actually need to use this. Yeah. We are more concerned about this later on. But for now, this is in total. That means overall, the standard deviation between the uh so the hold on just now it lags. Okay. So what we do is we look at this in total because this is the difference between your y and your y hat. Because this is the error, all right? That means you observe and you predicted. So but this is what we do. So remember, we want this to be small. Okay. So the question now is how sometimes to get it to be big, the value of the standard error can be big. So the question now is how do we make the standard error small? Yeah. What can we do if we want to make the standard error small? So what are the possible ways that you can do if you want to make the standard error small? Hmm. Chances is that if your standard error is big, that means the model will not be a good model. Yeah. But how do we say that okay, we want to try to make sure that the standard error is a bit small. So how do we do that? Okay, we can increase the n value, right? That means we can increase, yeah, that's one way, increase the number of observation. Okay, yeah, that's possible. Observation. What else? Yeah, supposedly this is like a very exclusive kind of process, that means you just cannot like have, and I mean basically you have already taken what is possible from the sample. So what else can you do? What else can you do to make sure that your standard error is quite small? So what can you do? Okay. So you got to think, right? Because this is what it is all about. Yeah, you have a data set. Sometimes you calculate, okay, you got a standard error which is quite small. All right. Suppose that you just cannot repeat the experiment. So how can we do it? All right. So that's for you to think. Okay. Okay. That is one way of yeah. This is one way for you to do it. Okay. Think how to do it. Yeah. All right. Be good thinking for you. Okay. So this is one thing, yeah, that we want to look at. Okay. So getting the standard error. Okay. So for that example just now, so we got our standard error to be 0.173. Okay. All right. So this is number one, yeah, that we have to consider. Okay, so like I said, it's not enough. Yeah, so you need to basically do a bit more. All right, carry out more tests to decide whether the model is okay or not. Okay, so let's look at the next one, which is the coefficient of determination. Okay, right. So the coefficient of determination measures the strength of that particular linear relationship, always denoted by the value of the R squared. Yeah. So R squared means the coefficient of determination. So it measures how strong is the relationship between the Y and the X. Okay. So let me give you an example. Yeah. Okay. So let's say this is what we have just now. Okay. And these are the points that you observe. Okay. Let's say you fit this line. So this is your fitted line just now. Okay. So this is what we have. Yeah. So now we want to see how much of the relationship between X and Y. So we need to say that Y is dependent on how much. That means how much does X contribute to Y. Okay. Now the R squared, because it's a square value, yeah. All right. Ranges between 0 to 1. Okay. This is the normal value that we have. Yeah. All right. So it's very between 0 to 1. Okay, so the bigger the R squared value, that means if your R squared tends to go towards 1, is a very strong relationship. Okay, now when your R squared is actually equals to 1, this is how it look like. When your R squared is actually equals to 1, if this is your fitted line, that means all the points, the observed points and the fitted one will be on the same line. That means it matches completely. Yeah, then this is what we call as your R squared is equal to 1. And most of the time we don't get it lah. This is almost impossible for you to get R squared is equal to 1. Yeah. Okay. Normally we get to be like this. Yeah. Now when your R squared is 0 means you have a scatter plot that looks like all over the place. Yeah. So for example, if you have a scatter plot that look like this, your points are everywhere in the world here. All right. It doesn't matter as long as they are everywhere. You cannot figure out any relationship. All right. Okay, so this may mean that your R squared is probably about 0, meaning to say that there is no linear relationship. You can't figure out what's the relationship is possible. Yeah. All right. So this is a value of 0. So how good or how strong is that value? That means what is considered as a good R squared value? That means acceptable value. Okay, normally if we get R squared about at least more than 65% or 0.65 is considered as already a strong relationship. Okay, what it means is that 65% of the model, yeah, is explained by X. That means X contributes 65% to the model. Yeah, so that's why we're looking at a higher value. If we say 0.9, that means Y is 90% dependent on X. Okay, the other 10% can be due to some variation. Yeah. Okay, but basically, this is what we are looking for. So if we say that R squared is greater than 0.65, that means this is already a good value for the R squared. Yeah, that means almost impossible to get 1. All right, I have not come across a situation where I actually get R squared is equal to 1. Yeah? Impossible. Most of the time I get a value between R squared 0.6 to 0.8. Yeah, so that to me is already a good indicator that Y is strongly associated with X, or X contribute about 60 to 80% the value of the Y. Yeah, so that's the value that we are looking at. So we want R squared to be high, we want the standard error to be small. Okay, so how do we measure the R squared? So this is how we measure the R squared. Okay, Okay, remember your ANOVA, yeah, in the last class, yeah. All right, ANOVA, remember? Um, okay, let me go back to that slide. Okay. In the last class, ANOVA, last week's class, I hope you still remember, we say SST is equal to SS treatment plus SS error. Error ni huruf kecil, tak apalah, SS error. Okay, right, and we say that SST is the deviation of Y with the grand mean, remember? Okay, we square kan summation, right? And we say that this one is the variation between groups, and we say that this one is the variation within the group. Okay, so this concept, yeah, of this variation between the groups within the group, all right, this ANOVA, okay, where this is split into this, is also uh, being considered in the regression. All right, why? Because we're looking at the sum of squares of the error. Remember, we are looking at SSE. All our assessment is based on the SSE, where we minimize the distance between the observed and the actual, yeah, sorry, observed and the predicted, yeah. So for that reason, all the this variation can be also translated into a situation of combination of two variation or two deviation. All right, okay. So what are the two deviation? Okay, so the two deviation is, now we still have the error, but we don't have the treatment, because we're not doing any treatment here, but we now have what we call as the SS regression. Okay, so let's look at what it is. All right, so the error just now we say was the difference, okay, between the observed and the predicted. Okay, this is our error. Yeah. Because when we calculate if you go back to that diagram, yeah, of your regression just now graphically, yeah, what we do is, remember, we have some values are being sampled, some values are not being sampled. All right. So in the SST, what we do is we take the actual value, we we minus the uh, average of the Y. Remember, if you look at the ANOVA pun, is Y minus the overall mean, the grand mean kan, and we square that. So this is the same concept. It's just taking the individual value, all right, divide by the overall mean of the value of the Y. So this is our SST. So we have Y minus Y hat, yeah, in this case. So that's why we have this Y minus the Y hat, because this gives you the variation with the overall mean, because this is deviation. So our error is the observed minus the predicted. Okay, because there is a prediction, all right, so this prediction will also vary with the Y bar. Remember the treatment, we say that we look at the um, mean of each group, we minus the grand mean. So this is the same situation. And we multiply that by n, yeah, because to get back what is the value for each of the group, yeah. So here, because we know the individual, so what we do is we take the Y hat, this is our predicted, minus the Y average. So this is our SSR. So these two combined together will give you the SS total. So this is how we are going to calculate our coefficient of determination. So we're just going to look at how do we actually calculate the SS R. Okay, based on this SSE we know earlier, and this is our SST. And how do we relate all this with the coefficient of determination? Okay, so this is what we do. Yeah, so the R squared is always calculated based on 1 minus the SSE over the SST, or it can be calculated using this formula. This is much more difficult, yeah, in the sense that you've got to calculate individual value of the y hat and then you minus the y bar. But most of the time we use the value of 1 minus SSE over SST. Why we do this? Remember, this can be calculated, this can be calculated. Remember, we have the formula for the SSE and we have the formula for the SST. So these values can be calculated. So for that reason, we always take R squared to be equal to 1 minus SSE over SST. Okay, what is SSE? Like I said, yeah, SSE just now, based on the formula, observed minus the predicted. So it's the unexplained variability in the Y, yeah. And the SSR, basically we have it Y hat minus the Y bar. That means how much is the variation of the predicted value that we get deviating from the mean of the overall Y value. Okay, so whatever it is, this is what we are interested to look at. So we want to determine the R squared based on the formula of 1 minus SSE and SST. All right, so we just want to see how much of the contribution of the dependent variable y and the independent variable x. So this is what we do. So we calculate the value of the R squared. Okay. Then if we look at the calculation, yeah, all right. So based on that formula just now, this is our y equation that we got the prediction. Okay. Okay, so to calculate the R squared, we need SSR over SST, or 1 minus SSE over SST. Okay, so this is a formula for your SST. Okay, formula for the SSE, you know just now, all right, which we calculated earlier from calculating the standard error earlier. So put in the value, everything, and put in the values. At the end of the day, we get 0.802. So 0.802 is very high. So we say that this is a very strong relationship because number one, we say that the what was the X, the production. Yeah, so the production actually contributes about 80% to the value of the dependent variable, the electricity consumption or something like that. Yeah. So this is how we actually interpret that. So we got to say that 80% of Y is actually depending on the X. The other 20% can be some other unexplained um, variation. So that means it's a good model. All right. So we get our standard error to be small. Okay, we got our coefficient of determination to actually be quite high. So this model so far is good because it fits the criteria of having a small standard error and having a strong R squared. See. Okay. Any questions? Yes, the R squared cannot exceed 1. No, not possible. Never. R squared cannot exceed 1. Okay. When we say exceed 1 means all the points lie on the line. Very nice, which is impossible. Okay. Any questions up to this? Any questions? You're okay? So we look at the second one, which is the coefficient of determination. Yeah. or the R square. And R squared, yeah, we want R squared. Some books gives the small value, I mean bukan small value, apa lowercase of the R, yeah. Alright, so R squared should be greater than 0.65, okay, to indicate a strong relationship. Yeah. Okay, any questions? Yeah. Okay, the soalan, any questions? You're clear on the two techniques? Okay, oh, this is the last one. Okay. Right. Any questions? No questions. I want to stop here. All right. We'll do the two other techniques in the next class. Yeah. Actually, you can calculate the beta naught hat and the beta 1 hat using the calculator. The calculator can give you the value. Okay. That's one way for you to actually get those values. Hmm. Yeah. Today we finish earlier. How to get from calculator? You got to go to the mode, the setting of the mode, okay, and then it says LR. I think you need to have the LR setting. Once you got the once you got the LR setting, then it should be okay. Then you just need to input. You can surf that from the internet. Okay. It's good to know that, okay, unless you can also use the Excel. Later, I will show you how to use the Excel. But you can do that from the calculator. Okay. Okay. The answer for first method should be small. Yes. Yes, Peggy. Yeah, that's right. For it to be a good model, yeah. The first method, yes, the standard error should be small. All right. The R squared should be higher than 0.65. Yeah. We do all. I think we have to do all. Yes, must satisfy all the four methods actually. It must satisfy all these four methods. Okay. Must satisfy all these. Yeah, it must satisfy all these four methods. Okay. So this must be done, this must be done, this must be done, and this must be done. Okay, we look at these two in the next class. Okay. Yes. So we need to check whether this is a good model or not. Yeah, based on all these four methods. So we have done today, we look at this one. So this must be small. This must be large, I mean big, but less than one. So this is what we look at today. If one method is not satisfied, then you will have to decide what you want to do. Yeah, sometimes you have possibility of one method not satisfied. Yes, possible. Then you decide what you want to do. Maybe you need to get more data or more observation, or maybe you want to you may need to consider. Okay, for example, let's say you have 30 sets of that observation. Then when you run all the tests, okay, then maybe one method tells, okay, let's say the R squared is just about 0.5, yeah, for example. So 0.5 is not really a strong relationship. So you may want to consider of, okay, relook back at the 30 set of data. Maybe you may just want to take, when you plot, again, there'll be some, okay, this is what we normally do, I think. All right, let's say you have some data that's like outside here, which the rest of the data is like kind of concentrated here. All right, you may have like some data which is like totally like you think is it could be something that is not relevant, so you may remove that. And that means, let's say from 30 you remove, let's say 5, so your sample now becomes, your observation now becomes 25. Then you may run it again to see whether it's a better or not situation. If not, then you may want to consider a different type of model for the model. When we talk about the linear model, doesn't mean that it is in the form of y is equal to ax plus b, but in reality it can also be an exponential relationship, because if you take the log, then it becomes, log y is equal to log a plus a b log x, for example. So doesn't mean that it is always in the form of y is equal to mx plus c2 is always in that form. You do a little bit of transformation, you may be able to transform the exponential to become a linear by taking the log. So that's why this actually linear regression is one of the favorite type of modeling lah that people always try first, because of its robustness. She's quite robust. So you maybe with the simple you may not see it, but more when you do in the next chapter, which is on the multiple, then perhaps you should be able to see a bit better. Okay, yeah. So typically we have to do the four method, but the four method is actually quite simple. It's not that that's why I said the best thing normally whenever we have the regression, we either run it on the Excel or some MATLAB or some statistical software, because that will give us the whole lot of what we are looking for. Okay, right, any other questions? Yeah, yes, I will show you. Okay, I will show you how to do the Excel. Show you how to do the Excel, because I always feel that you have the tool, just use it. Okay, it's just like you have the calculator. I'm not I my understanding is very, to me it's very simple, in the sense that you just need to know how the values are calculated. But at the end of the day, if you have a tool that can help you to achieve those values, then you just use it. Because fundamentally, you should know lah, when I say the Excel will give you all the beta naught, beta 1. But at the end of the day, you must know, okay, beta 1, how do you get the value of the beta 1? It's just by minimizing the error. So the technique we use is we minimize the error. That's how we get the value of the beta naught. And how do we get the standard error, for example, is by taking the error divide by number of observations minus 2, n minus 2 in this case. So what do we do? What we do is just we're looking at the smaller the standard error, means that the gap between the y observed and the y predicted is quite small. So because at the end of the day, you want to know what to what to tweak, what is it that you really want to do in order to get a better result from the data that you
start
have.
the
Sometimes
new
you have a lot of
chapters
data, but
right
you may
now.
not want to use the
Okay.
whole lot of the data. All right.
All
So
right.
that's why you
Okay.
need to
We are
understand
in
the
the heat
fundamental. But
exchanger
doing the
topics. So
calculation, to me,
it's
the
only,
calculator or
we have only
Excel,
chapters
if
to
you can
cover
use,
all the
or any
topics
other
under heat
tool you can use,
exchanger.
it's okay. To get the beta naught and the beta 1, you just plug in the calculator will give you what is beta naught, what is beta 1. But at the end of the day, you must know what is actually beta naught and what is beta 1 and how do we actually get the beta naught and the beta 1. That is understanding the concept. Okay. Okay, any other questions? So tomorrow is the quiz, yeah? So please take note of that, okay? It's MCQ plus a little bit of calculation. So make sure you have your calculator, because this is on the hypothesis. So you make sure you have all your statistical tables ready and whatever lah next to you so that you'll be able to calculate. Alright, nanti tak kelang kabut nak cari statistical table and stuff like that. Yeah. So please take note of that. Yeah. So it's MCQ. So you just need to answer on that values lah. I mean, not values, on the ULED itself. Okay. All right. So probably about 30 minutes or so. All right. 25 to 30 minutes. Then we will get it done tomorrow morning. Okay. So if you do not have any questions, so I want to stop here. Yeah. And then we'll do the two methods tomorrow. Okay. Okay. So far, okay. Can you follow? I mean, we're already almost leaving only probably tomorrow we can finish this chapter if you have no problem. So leaving only one more chapter to go. All right. So do you understand what is it all about? I mean, I hope you understand what I'm trying to tell you, but I do not know whether on your part you really understood. I hope that you'll be able to use all these techniques, whenever you do your work in the future. Because or else there's no point for you to learn if you're not going to use it. All right, you need to know when to use the ANOVA, when to use the two population test, when to use the regression. I think regression is very widely used. Yeah, so I think that would be good for you. Okay, any other questions? No, you're fine. Okay, all right. Okay, Afiq, okay, no question. Amanda, Amiruddin, Alia, Ajit, Zainara, Ravin. Okay. Yeah, normally you always ask me a question, Ravin. Okay, this time the last few lectures have been quite quiet. Okay. All right. Okay. All right. Okay. Okay, so if you do not have any questions, so I will stop here. Okay. All right. Now, yes, I will do the same thing. Yeah, the pages for the quiz will also appear. I think 5 questions for each page. Yeah, so